Orientation and navigation. Background. The Haida of the Pacific Northwest in Canada recount a legend in which the daughter of a tribal chief dreams of a large, shining fish that leaps out of the water. She longs desperately to possess this fish that has never been seen, even by the elders in her village. She cries and cries until she grows sick with grief, so her father calls together his tribal council to ask their advice. A wise old medicine man brings forth a raven, who explains that he has seen such fish far, far away, at the mouth of the mighty river which leads to the village inlet. To show his loyalty to the tribe, the raven offers to bring one of these fish back to the chief's daughter. He flies directly to the river mouth, dives into a swarm of fish, and rises with a young salmon in his talons. By chance, he has caught the son of the salmon chief, so, as he turns to fly back to the village, salmon scouts jump out of the water in great arcs to see the direction in which he is flying. Led by the chief, a horde of salmon swim up the river in pursuit. The raven, arriving far ahead of the salmon, places the fish at the feet of the tribal chief's daughter, and then tells the village members to prepare nets across the river to catch the salmon that will soon arrive. When all of the fish are caught, they are strung between a rock and a large cedar, which then becomes a totem pole. The totem is carved with both a raven and a salmon to honor the animals that have brought such abundance to the tribe. Since that time, the salmon return each year to the village, swimming rapidly and frantically against the river current in an attempt to rescue one of their sons. This tale, The Coming of the Salmon, provided the Haida with an explanation for the collective and seasonal movement of one group of animals in their environment. Other people, in different parts of the world, have generated similar stories to explain why animals undertake long and often arduous journeys. In the 19th century and the 1800s, many Europeans believed that birds spent the winter hibernating in mud at the bottom of lakes. Although it now seems far-fetched, it was probably more believable than the idea that small birds could travel from Europe to Africa and back again in 1 year without getting lost. At that time, most people traveled very little, and they had few ways to access information from other geographical locations. Today, many people visit different parts of the globe and are able to observe animals in their natural habitat, either directly or indirectly through video recordings. It is also possible to follow animal movement, even across vast distances, using technologies such as global positioning systems, GPS, and radar tracking devices. This information has been invaluable in studies of how and why animals move through their environment, although many questions remain unanswered. Chapter Plan. This chapter focuses on spatial behaviors, examining how humans and animals are able to move through their environment without getting lost. Even very simple organisms are not stationary, and many humans and animals spend a large part of their waking hours traveling from one place to another. The ability to do this effectively and efficiently is critical for a variety of activities. Foraging or hunting for food, searching for mates, caring for young, and returning home afterwards all depend on cognitive faculties that direct and control spatial movement within familiar and unfamiliar environments. The chapter will discuss a range of spatial behaviors from basic orientation responses to complex navigational feats of migration. The first section outlines evolutionary explanations for these behaviors, which are typically divided into processes of orientation and navigation. Cognitive mechanisms of orientation point animals in the right direction. These are described in terms of kinesis and taxis, two of the simplest spatial responses in the animal kingdom. The next sections focus on navigation, which is divided into small-scale, short-distance, and large-scale, long-distance travel. Sections 5.3 and 5.4 consider issues such as how different species compute the distance and direction of travel, and what they understand about spatial relationships in their surroundings. The final section of the chapter describes the neuroscience of spatial behaviors with a focus on neural systems that mediate small-scale navigation. Finding the way. Animals do not search randomly for food or mates, nor do they rely on chance to return home afterwards. Rather, natural selection has favored cognitive processes that facilitate the ability to find the way, both to and from specific locations. This first section outlines the adaptive significance of finding the way. Ultimate explanations for why animals are able to move through their environment without getting lost. How this occurs is described in the subsequent 3 sections, 5.2 to 5.4. Getting there and knowing where. Finding the way can be divided into 2 distinct processes, getting there and knowing where. Getting there depends on an elementary system that directs animals toward different, often unknown, locations. Virtually all organisms display some form of this behavior when they orient to places where they may find food, mates, or new habitats. Even bacteria get somewhere new by moving from areas of low to high nutrient content. The getting there system operates by initiating motor patterns in response to internal signals, such as hormones, or to external stimuli, such as sensory cues. In contrast, the knowing where system allows animals to reach a particular destination, regardless of a current position. It relies primarily, although not exclusively, on previous experience to identify the goal location. Knowing where allows animals to locate hidden food stores, to find the way around familiar environments, and to travel back and forth between seasonal habitats. Spatial behaviors guided by either getting there or knowing where often appear to be goal-directed. This is particularly true of the latter, as animals searching for food or returning home seem to have a predetermined destination in mind. However, even if animals consistently arrive at the same place, this does not prove that they had the intention of doing so. In many cases, the cognitive mechanisms that signal when to stop control behavior at the end of a journey. In other words, animals don't know that they have arrived until they get there. This issue is discussed in more detail throughout the chapter. Although they will be discussed separately, the processes of getting there and knowing where often operate together. One example is dispersal, the movement away from a parent or conspecific population due to declining resources, overcrowding, or mate competition. Dispersal generally involves movement to an unfamiliar environment, but animals seldom wander aimlessly as they find their way to this new home. Dispersing animals must possess cognitive mechanisms that direct their travel, i.e. getting there, and help them to identify suitable ecological conditions when they arrive, i.e. knowing where. Without these in place, the advantages of dispersal, i.e. finding a better habitat, may not outweigh the disadvantages, e.g. energy resources required for a long journey. Adaptive value. The adaptive value of finding the way is examined most frequently in terms of 2 behaviors, caching and migration. Caching allows animals to hide a valuable resource, usually food, when it is plentiful, to be retrieved at a later time when it is not. Not all animals cache food, although the behavior is displayed by a variety of birds, mammals, and insects. One of the most impressive is the caching ability of Clark's nutcracker, Nucifraga columbiana, an avian species that hides seeds in up to 10,000 separate locations, which it then recovers a year later. If evolutionary pressures have shaped the behavior, caching should be more pronounced in harsh environments where food is less plentiful at certain times of the year. This hypothesis was verified in a comparison of 4 corvid species that inhabit different ecological zones of the San Francisco Peaks in Arizona. Clark's nutcracker and pinyon jays, Ginmorinus cyanocephalus, which live at the highest elevation with the most severe winters, cache a larger number of seeds than Mexican jays, Aphelocoma walworberry, and western scrub jays, Aphelocoma californica, which live at the lowest elevation. Caching is a labor-intensive activity, so it would not be adaptive if animals were unable to locate their hidden food in the future. Stated as a scientific hypothesis, species that depend on cached food for survival should display superior memory for spatial locations. Figure 5.1 shows the results of an experiment testing this idea, in which performance in a spatial memory task increased across the 4 corvid species that inhabit progressively harsher environments, Olson et al. 1995. The findings could not be explained by differences in general cognitive abilities because the same species performance relationship was not apparent in a non-spatial memory task. Compared to the other two species, Clark's nutcrackers and pinyon jays also have larger wings and bigger bills, both of which facilitate the transport of seeds over long distances. It seems likely, therefore, that both cognitive and morphological traits evolved in these species in response to the ecological challenge of reduced food availability during particular seasons. Figure 5.1 Spatial and non-spatial memory in 4 corvid species. A. When tested in the lab, Clark's nutcrackers outperformed 3 other species in the crow family on a spatial memory task. B. In contrast, this species did not exhibit superior abilities in a non-spatial memory task, remembering the color of a circle. Because they live in a harsher environment than the other bird species, Clark's nutcrackers must rely more heavily on cached food sources to survive. Okay, so there's 2 graphs. In the first one, the x-axis is block 100 trials, and it's showing numbers from 0 to 18. And on the y-axis is retention interval in seconds from 0 to 50. And this is a spatial task. And then the 4 dotted lines are from the scrub jay, Mexican jay, pinyon jay, and Clark's nutcracker. Okay, so the scrub jay doesn't retain a spatial task for very long, but Clark's nutcracker, wow, it's way above all the other ones, and it's the farther north one. And in the non-spatial task, in the second graph, so again, there's a block of 100 trials on the x-axis from 0 to 35 this time, and on the y-axis is retention interval in seconds from 0 to 50. So on a non-spatial task, it looks like the pinyon jay performs the best, then the Mexican jay, but they're like fairly similar. Whereas in the first graph with the spatial task, the Clark's nutcracker performs way better from the harsher environment. Differences in spatial memory related to ecological pressures have also been observed between subpopulations of the same species that inhabit different environments. For example, black-capped chickadees, Poecile atripala, from Alaska exhibit higher rates of successful cache recovery in the lab than do chickadees from Colorado, where the winters are shorter and less severe. Not all studies, however, report better spatial memory in caching than in non-caching animals. Indeed, data summarized across a large number of these studies indicate that the findings should be described as supporting trends rather than conclusive results. Smulders et al. 2010. Smulders and colleagues go on to suggest that the adaptive significance of spatial memory should be examined by considering which components of this cognitive process reflect the natural history of a species, that is, the duration, capacity, and specificity of spatial memory should vary with the ecological constraints of an animal's natural environment. This appears to be the case in that animals retrieving caches during extended periods, e.g. up to 1 year or later, show the longest memory retention for stored locations in the lab, and those with the greatest number of caches in the natural environment can remember the most locations of hidden food. This approach, identifying which components of spatial memory should be affected by specific ecological pressures, has helped to uncover evolutionary adaptations of spatial memory, although many questions remain. One of the most controversial is whether evolutionary pressures have led to sex differences in this cognitive process. See Box 5.1. Box 5.1, Sex differences in spatial memory. If spatial memory is shaped by natural selection, there may be sex differences in this ability because evolutionary pressures to find the way are different in the two sexes. For example, males often spend more time and travel a greater distance than females when they are looking for food or potential mates. This is reflected in animal experiments that consistently report a male advantage on tasks, such as the radial arm maze, that rely on memory for the spatial layout of an environment. Interestingly, there is no sex difference on this measure for species in which males and females show similar patterns of territory exploration. Male meadow voles, Microtus pennsylvanicus, have a home range up to 4 times larger than females, whereas the home range size is similar for male and female pine voles, Microtus pinotorum. Male meadow voles, but not male pine voles, outperform female conspecifics in lab tests of spatial memory. The male advantage in spatial memory is frequently offset by a female advantage in object recognition. In tests of this process, animals spend a few minutes exploring an environment that contains two objects, e.g., small Lego constructions. After a delay period, they are returned to the environment where one of the objects has been replaced with a new one. Object recognition is measured as increased time exploring the novel compared to the familiar object. Female rats and mice outperform males on this task, suggesting that they have better memory for the unique features of cues in their environment. This would explain why females, but not males, make more mistakes on a radial arm maze task when objects within the maze are randomly moved. In contrast, performance declines in males, but not females, when the objects stay in the same place, but the overall geometry of the testing environment is altered. Similar patterns of sex-related differences have been observed in other animals and in humans, Sandstrom et al. 1998, leading to the idea that males rely more heavily on cues that provide global directional information, whereas females are more sensitive to information about the position of uniquely identified cues. These differences reflect averages with large overlap in the distribution of scores for each sex. Thus, one cannot assume that any one woman will have better cue and worse directional-based spatial memory than any one man, and vice versa. Nonetheless, the overall pattern of results suggests that sex differences in finding the way, originally described as a male superiority in spatial memory tasks, see Figure 5.2, are more accurately interpreted as a preferential reliance on directional cues in males and positional cues in females. An ultimate explanation for this distinction is based on a hunter-gatherer division of labor. Males inherit cognitive processes that promote hunting, whereas females inherit those that promote gathering, including the ability to identify and remember the location of edible plants. As with caching, ecological pressures have shaped how animals are able to find the way during migration, the seasonal movement between spatially distinct habitats. Migration is a timely and physically challenging endeavor. The cost is enormous in terms of additional energy required for the journey, as well as potential problems along the route. These disadvantages must be offset by fitness advantages in the new habitat. A case in point is that many birds spend summer months in northern Canada, where they can feed on immense populations of protein-rich insects over long daylight hours, but then travel to more southerly locations when these conditions decline. As with this example, selection tends to favor migration when there are predictable variations in environmental conditions across seasons. In all likelihood, short-distance migration preceded long-distance migration in that specific groups of animals begin to travel further over successive generations as their environments and the resources within them changed. During this evolutionary process, physiological traits that facilitate long-distance travel emerged in some species. These include a larger wingspan in migrating birds and an increased capacity to store fat in most migrating mammals. No doubt, cognitive processes supporting migration also evolved in these species. Consistent with this idea, memory for the spatial location of a feeding site persists for at least 12 months in garden warblers, Sylvia borin, whereas the closely related but non-migratory Sardinian warblers, Sylvia melanocephala, retain the same information for only 2 weeks. Further comparisons of migratory and non-migratory species are likely to reveal other differences in cognitive processes related to migration. Flexibility. Finding the way, both getting there and knowing where, involves some level of flexibility. Caching is an obvious example, as animals must be able to hide and retrieve food in different locations and at different times, depending on food availability and weather conditions. The same is true of migration. Journey onset is shifted if weather conditions are unfavorable, and animals may detour around storms or alter stopover locations if feeding grounds are overcrowded. Over repeated journeys, migrating western marsh harriers, Circus aeruginosus, exhibit less variability in departure times than in routes taken, suggesting that cognitive mechanisms controlling the direction of travel are more flexible than those controlling its timing. Migration itself is flexible in that closely related species, as well as subpopulations of the same species, frequently display contrasting migratory behaviors.